ask the question, basically, how do we produce a water-repellent surface? So the best way, if you want to ask questions like that, is you look at nature and see how they do it. And we'll see what they do is they basically use waxy surfaces and then they make them very rough. And this discourages wetting because there's basically a high energetic cost of the fluids wetting the solid. So that's all very good in vague terms, but how do we quantify it? How do we, and what is it that makes something water repellent? Is it simply the contact angle, or is it the ability, really when we think of water repellent, we want a raindrop to hit the surface and then roll off it, right? So that's really the principal dynamical constraint, is we don't want drops to stick to solids. So this is a big field, has been in the last decade, owing to advances in microfabrication techniques, so they can now make surfaces with texture on the micron scale reliably, and so it's opened up the possibility of this creating biomimetic water repellent surfaces. Biomimetic simply meaning copied from nature's designs. Okay, so just to remind you of what we've seen so far. So from lecture 3, so we looked at So we looked at the following situation. We looked at a fluid on a solid. We defined an equilibrium contact angle. Okay, and so the simplest way to see it is from the horizontal force balance at the contact line. But you can also see it by looking at the energy of moving the interface. Okay? So basically I have these three tensions. And the force balance gives the horizontal force balance gives Young's equation. Okay, so we can also think of this in terms of energetics, and this will be useful when we start looking at rough solids. So we imagine this interface moving, then doing so changes the energy, the surface energy of the lower substrate by an amount proportional to the distance that it's moved, and there's also associated creation of surface. Okay, so this is again our equilibrium contact angle. So right. Okay, so this is the surface energy. This is again the change from the moving okay, so this is a change in surface energy associated with this element, wet or dry. So again, so this is our fluid phase here, our liquid. Then we have the additional surface energy from creating the surface. Okay, so in equilibrium, we want this to be 0, which then gives us Young's law again. Okay, so that's a very simple view, and it would be nice if that was all there was to it, the wetting of solids by liquids. But alas, there's complicating physics in the form of contact angle hysteresis. Okay, so it's simply an observation that there's a finite range of contact angles. Static contact angle. So for a given solid, liquid, yeah.
Where do you have this difference between what used to be solid, liquid, and now is solid vapor, right?
Yeah.
And then you have a term for creating interface.
Yeah.
So you're saying that the size of the interface, the gas, liquid interface increases?
Yeah. Yeah, so that's not, it just sort of depends on the geometry, but locally that should be true. Right? So near the interface. Okay, so we have, so this is just an empirical fact. One sees that there's a maximum and a minimum, and we can see this experimentally. Okay, so we have so basically many static contact angles can coexist. And this is going to depend on the chemistry. And it's also going to depend on the roughness and the history. Okay, so let me just convince you that this is a viable. So this is basically the way it works. So if you take a fluid drop and you pump it up, so if you believe what's written on the left, there's a unique equilibrium contact angle. But if we pump fluid in, then the drop expands, and these contact lines remain pinned. So you start with an equilibrium value. They remain pinned, and so as you fill the thing up, the static contact angle increases until it reaches this advancing angle, and then the thing starts moving, right? So then the contact line moves. Similarly, if we start with an equilibrium here and we draw angle and we draw fluid out, then the static contact angle decreases until reaching the retreating value, and then the contact line starts moving. Okay? So we can see this in a video. we do this, so show large size. Oh, that's too large. Oh! So we're going to do exactly that experiment, which I just showed the schematic of, which is pumping up a drop sitting on a surface. Okay, here we go. Okay, here we go. Here. This won't be too ridiculously large. That's okay. So we pump it up. Start off with a drop at an equilibrium value, and you see that these angles increase, and then the thing spreads. And now, if you draw fluid out, there will again be so there's actually a finite range of angles in which the thing is static. But if you exceed the advancing angle or the receding angle, then the then the situation becomes dynamic and the contact line is no longer stable. Okay, so
if you in between those angles, if you stop, will it go back to the original angle that we calculated to?
In between, so it's happy anywhere between the advancing or the retreating, right? Like it'll just sit there.
If you pull down your little straw there, then
Yeah, so at any given time, if it's static, it will remain static. It'll only become dynamic if you exceed the...
But if you stop the pumping, say,
yeah.
will it pump up the straw, or will it equilibrate, right?
What I'm saying is, I would...
Right, if you're in between.
So here you...
Will it pump this fluid back up the straw?
It would like to. It would, yeah. It would tend to. I mean, it means the pressure's gone up inside. Yeah.
A little bit of the straw, right?
Yeah. But you can remove the straw, right? I mean, you can add fluid as much as you like, and it will go to an equilibrium value, and the static contact angle in that equilibrium will be somewhere between the advancing and receding. That's all you can really say. Okay. And so you can ask, well, what's the origin of this, right? We've just used a simple energetic argument to say that there should be an equilibrium angle, but there isn't. And so what's actually happening is the following. So as the contact line advances, it's not actually, so our idealized picture is that it's moving on a perfectly flat substrate, but in reality there are always roughness elements, okay? And so as this contact line advances, it basically gets snagged on roughness elements, on impurities, so there can be junk down on the surface, so either chemical impurities or texture. And as the contact line moves, it gets snagged on it, and so basically becomes irregular. So what you have moving along here is not a perfect plane, it's a rough surface, and this corrugation is energetically costly. We know that whenever you create surface area, there's an energetic penalty. So this indicates that there's an energetic penalty to moving a contact line. So what this is basically drawing a rough plate. So this is a very small scale. I'm not exactly sure what, but we're basically pulling it out of a bath. So you can see that the front is not a perfect line as a result of these inhomogeneities on the surface. And so it basically has to do with the reason we have this contact angle hysteresis is because surfaces are not perfectly clean or perfectly smooth.
So if you take a real surface, you can then speak of theta E. There doesn't.
Yeah, so there's a chemical equilibrium angle which you can define, but then the details, exactly. But then, exactly. So the range will then depend on how clean the surface is and how rough it is, because both chemical inhomogeneities and textural ones will cause this effect. Okay, and so it's kind of interesting. So in order to kill the contact angle hysteresis, and we'll see why you might want to do that in a moment, you want to make the surface either really smooth, so you have no such heterogeneities, or you want to make it really rough. So there are two ways to go. Okay, so let's.
So if you put two drops into a real surface, you will observe them at different angles.
Yeah, you can do. Yeah. Okay, so one thing you can see immediately is if you have this range of angles, if you have a roughness, if you have a corner, so let's just imagine we have a surface which is not quite planar, say it looks like that, then we have a fluid advancing and it has a contact angle, say, so this is our corner, it has a contact angle of this, say, relative to this, so that's theta E, this is our liquid. Then as it advances over this thing, then it can actually flip over at this point here. You can say, well, what's the equilibrium contact angle defined in terms of it? Is it defined in terms of this surface or this surface? So if you define it in terms of this surface, then it can go something like this, right? So you have this large range of admissible contact angles, so all the way from here to here as you go over a corner. Okay, so you have an ambiguity in the contact angle, and so this is why contact lines tend to get pinned on edges. So, and this is why you can overfill a container. It's basically the contact line gets pinned. Okay. So when it, and this is consistent with, so roughness elements, there's basically there tends to be pinning of contact lines on roughness elements. Yeah.
Yeah, one thing, so hysteresis for me has to do with loading and unloading.
Yeah.
So
Yeah.
how's it, what is the,
So depending on whether you're, so it depends on its past is the way I think about it.
right.
On the memory, if you like. So whether you've filled it up from below or from above, for example, you can have a drop with the same fluid, and depending on its past, which way you've loaded it, the equilibrium contact angle can be different.
The contact angle will be different.
Yeah.
Okay.
Yeah. And so, right. So okay. So who cares about contact angle hysteresis? Well, if we have a range of contact angles, then it causes drops to stick. And again, if you're trying to design a water repellent surface, you don't want drop sticking. If a drop sticks to a metal wall, then it's going to tend to rust, right? You're going to get oxidation, which you don't want. There are many other situations, and particularly in biology, a lot of processes require access to air, and they don't want to be wet. So the leaves don't want to be wet, or they can't photosynthesize. And so you want to be able to repel drops. But if you have this contact angle hysteresis, then if we have a drop on a solid, if we tilt it, then you can have a range of contact angles. So basically this is going to increase up to the advancing angle, this can go down to the receding angle, and because of the difference, there's this pinning force, right? So it's basically stuck until it reaches a critical angle, and then the thing goes, right? And that critical angle is going to depend on the size of the drop, right? Because if you think of a drop stuck, say on a wall, if it's symmetric, as this would say, right? This would say that this equilibrium contact angle is just the contact angle is just the equilibrium one. So how do you do the force balance? Well, you say mg downwards is matched by the net tensile force upwards, which, if it's symmetric, is going to be 0, right? So if you have a unique contact angle then there's no possibility of supporting the weight of the drop, so it will just fall. But now we have the situation where the drop actually looks like this, or can look like this, where this is now the retreating angle, this is the advancing angle, and you can still have a static situation. So then the net force you get by integrating the tensile force around the contact line, and you see that this contact angle hysteresis can support the weight of small drops. So that's what we just saw there, and we can see it again. And of course, there's going to be a size at which it doesn't work anymore. So here there will be a critical angle, and this is how you can measure the contact angle hysteresis, right? Basically know the size of your drop, and you measure the angle at which the thing starts moving. Okay, so small drops, of course, these contact angle hysteresis is going to give rise to a force which is comparable to the capillary force. So we expect small drops, that is to say drops small relative to the capillary length to be able to stick, whereas large ones will roll, and that's what we see here. So, okay, so we've just seen this, and we basically argued about this. So on your problem set, I ask you to do let me get to look at a slug of fluid in a tube, which is actually the easier geometry. So it's basically looking at this. So you have a slug of fluid, and owing to the possibility that this can be different from this, you can have the weight supported. So you can basically, if you know the equilibrium contact angle, again, the argument is that this can increase up to the advancing angle here and back to the retreating angle here. And so you'll get a net force, and you can calculate the net force and see how big a slug you can support as a function of, say, the tube size. Right? Okay, so it's similar conceptually to this. Again, the argument is that so the maximum force, you're going to get the maximum force, that is to say, sort of basically, this will change shape in a static way until you get to this stage, and then if this contact force is not sufficient to support the weight, then it will move. Okay? Yeah?
Actually, based on this drawing, why in that case the bottom curve is not convex instead of concave?
Yeah, it sort of depends on what the mean is, right? So as long as it will be larger. This one's sort of very easy to see, but yeah, I should draw it so that.
Can it be like this also? Or
yeah, as long as this is bigger than that one, right? So we know that the equilibrium value is.
Oh, of the angle theta A, you mean?
Yeah.
Oh, okay.
Right.
As long as that's bigger.
Yeah.
But it could be also like this, right?
Yeah, I mean, as long as there's a difference in them.
Right, like a hanging valley.
Yeah. So, okay, so we now sort of understand the origins of this. So again, it's the microstructure of the surface which is giving rise to this contact angle hysteresis. And so there are actually models. So De Gennes did models of a moving contact line, and so if you have, say, he looked at the case of sparse defects. So if we have an interface moving across the surface which is smooth, but it has the occasional defect which looks like this, then you're going to get your interface is going to be distorted, and it looks sort of, I think you had sort of like a horn shape like this. And so you basically calculate the surface area of that, and so that's going to be the energetic cost of moving past this heterogeneity. So you can actually get a quantitative feel for the energetic cost of moving past this roughened surface. But you have to have some model of what the defects look like and how it pins. But okay, so that is basically the origins of contact angle hysteresis. Is the is the distortion of the contact line on the microscale, and so the art of water repellency is preventing drops from sticking. So if we want to prevent drops from sticking, we want to decrease this contact angle hysteresis as much as possible, right? And so how do we do that? Well, we can imagine from this argument that we have. So again, it's best to think, typically things are like this. So you have junk, heterogeneities, and these can be in texture or chemistry. So most surfaces are rough. The only thing that isn't is glass. Glass is one thing which you can get smooth down to sort of a 5 micron scales, 5 microns or even smoother. But in any case, as this contact line moves along, it gets caught on the heterogeneities, and so this corrugation of the surface energetically costly. Okay, so we want to get around this, and the best way to solve problems like this is how do you create a water repellent surface? You look at nature, and so nature has solved this problem. Again, many plants want to stay dry, leaves want to stay dry in order to photosynthesize, and so they will have structure. Have you ever seen a drop rolling on a lotus leaf? It rolls as if there's no friction whatsoever. Okay, and this is because of its texture. So down to the micron scale, you have so basically bumps. And you see these bumps have bumps, and the bumps have bumps. So you have this hierarchy of texture, and also the surface is waxy. Okay, so water doesn't like to be on wax. The contact angle is high. So just from the fact that it doesn't want to be on wax, if you make a waxy surface very rough, then there's a huge energetic cost of wetting, right? So if the drop is going to actually impregnate all of the roughness elements in the wax, there's going to be an enormous cost. It will tend not to. It will tend to bead up on the surface and then roll. Okay. Okay. So now we want to start thinking about how we can quantify roughness, the effect of roughness on wettability. So it's a question of how to overcome this contact angle hysteresis. And of course, keeping things very clean and very smooth is very hard, but it turns out by making them very rough, you can solve the problem. Okay, so you can ask the question, if we have a rough surface and we're in contact with a bath, we have a surface tension gamma. When is this fluid going to wick up here? Okay. So think of these things as islands on a planar surface, so we basically have bumps. And I can just as well turn this sideways. We're not going to worry about gravity. We're on a scale where gravity is not important. So R, so is the total surface area over the projected surface area of this roughened surface. So basically take the surface of the islands plus the surface of the substrate to get R and compare it to the planar area. So this is necessarily always greater than 1. And then we have the second roughness parameter, which is the area of the islands. So the top of the islands over the total area. So this is necessarily less than 1. Okay? So these will come up in our musings here. So if we imagine how much energy we get as this thing advanced by an amount delta Z,
projected area means this area is with all the heights of the islands.
yes, yeah.
Squeezing the islands out.
Yeah, just imagine you look down from above and...
The sides, you're ignoring the sides of the islands.
That's right. Yeah, yeah. On this one. Yeah. Yeah. Tops of the islands. Yeah.
So that one is the top of the island, and the other one is the side of the island that we're not counting projected.
Yeah, so this is the
projected
total area. That's right. Yeah. dz. Okay, so if this thing advances an amount dz, then the change in energy is going to be, so let's define all of these. So this is gamma solid liquid, and this is gamma solid vapor. Okay. Okay, so we have two components. Okay, so we imagine, so what we're doing is we're comparing this to this. So we're imagining the fluid is going up and filling in the regions between the islands. Okay? Okay, and so this is going to happen depending on the chemistry and the texture. And when it does happen, so it's going to happen if you decrease. So this is called spontaneous wetting or demi-wicking. So again, wicking is when you have a candle. I think we went through this. When you have a candle, right, and fluid is drawn spontaneously up, and it's because it's very fibrous, and so there's capillary. It's very rough and fibrous, and the capillary action pulls the stuff up. So this is wicking when this change of energy is less than 0. So if it's energetically favorable for the fluid to climb, then it will do so. And so this is the equilibrium contact angle, which we know from Young's law. So when this is greater than some critical value, which depends on the shape. Okay. I'm going to call this cos theta c. Okay, and so this is going to go spontaneously if the equilibrium contact angle is below this critical angle. Okay, so we know basically equilibrium contact angle, if it's low, the thing likes to wet, and so if it's low enough, it's going to go spontaneously, and the critical value at which it goes depends on the texture. Okay, so we can basically decide whether or not a fluid will spontaneously wet a surface by changing the surface, texture of the surface. Okay, so we know that we can control, so the chemistry determines theta E. Right, so basically the components of so the chemistry of the solid, the liquid, and the gas will determine theta E. That's just a chemical property of the three phases. And so so we can control this with chemistry. We can control R and so our two texture parameters with geometry. So we can prescribe the wettability of a surface. Okay, so if we have a very rough surface, so we can, if this number is huge, if R is much greater than 1, then we can see that theta c goes to pi by 2. So we have this wicking phenomenon, this spontaneous motion, spontaneous wetting, whenever cos theta equilibrium is greater than 0, which is simply saying that theta E is less than pi by 2. So whenever you have a surface, a fluid which has a tendency to wet a surface, roughening it will give rise to wicking. So if this is, for example, if we're looking at water, then any okay, and the other limit, if we take the limit of R being small, of course, its limiting value is 1, not 0. So if the surface is nearly flat, then you get wicking when cos theta E is greater than 1, which is to say never. Right? Okay, and so the last thing, so most solids are rough. So this is a concern. So this is smooth glass is smoothed down to angstroms, actually. Smooth down to 5 angstroms. That's why I have notes, because I never remember numbers. Okay, so let's press on. So this is we have now a criteria for spontaneous wetting. See that there's another possibility, which is that the fluid really doesn't want to wet the solid. So in the opposite case, in fact, the case that we want for water repellency is the case where the drop beads up and does not impregnate the roughness elements on the surface. So but this number will come back at us, this theta C. So there's going to be a crossover between these two states, one in which the fluid wants to get into the roughness elements and wet everything, and one in which it wants to avoid it. So we want to be able to define that, define the dividing line between those two states. One thing I can perhaps mention so we're sort of coming up on this slide now. So we're going to see that there are two different states according to whether the fluid penetrates the solid or not. And basically it turns out this is going to be what you want. This is what the plants achieve for water repellency. And the reason this is desirable is that this decreases delta theta. Here is the contact angle hysteresis. Okay, so it turns out that this, you can also get very high contact angles in this situation, as we'll see. We'll derive all these equations. But the contact angle hysteresis actually increases it in this situation when you have the spontaneous wetting. And so if you want a drop to roll off a surface, as on your Gore-Tex jackets, you want this to be the case. Yeah? And so we basically want to be able to distinguish between these two cases by looking at the texture and the chemistry. Okay, so if we have a flat surface and we roughen it, so what happens? Okay, so we can define, so let's imagine, so we're imagining here this is basically a drop with the, say, raindrop scale, millimeter in scale, and we have roughness on the scale of 1 to 10 microns. Then we can define an effective contact angle. Of course, it's just a sort of a mean, right? Because locally, you're going to have this, but it can be stuck on a corner. It'll depend on the local topography. But basically, just by looking at it with a microscope, you can see, you can zoom in and see what this looks like. Okay? It's sort of like a macroscopic contact angle. So let's define that. Okay, so just observation. Okay, so if the equilibrium contact angle is, as in this case, less than pi by 2, which is to say, let's just to say we're talking about water to make the language simpler. If this thing is hydrophilic, it will become more so here. Okay? So that's to say, so it wants to wet it, it'll want to wet it even more if it's rough. And that makes sense because, again, if it wants to wet it, it's going to want to wet it even more if it's rough, because if it moves a little bit, it actually wets more surface, so there's more energy release, right? Okay, and if you have, if you have the opposite case where you have a hydrophobic surface, so if the equilibrium contact angle is greater than pi by 2, then it's going to become even more hydrophobic. So that's basically, you're going from this then the thing's really going to beat up, right? With a very small. Okay, so both of these indicate the hydrophobicity hydrophilicity. So this is hating water, liking water, enhanced okay, so whatever the tendency of the surface, roughening it is going to accentuate that, right? And so again, in the case of plants, plants are waxy, which makes the contact angle greater than pi by 2, and then by making them waxy and rough, you accentuate that tendency, and so you really increase the contact angle. Okay?
You showed us insect that had like little spots that were hydrophilic in order to
Yeah,
rough.
yeah.
Is that only controlled by roughness, or is it also?
They also use chemistry, so they can excrete things which will change their wetting properties. Typically, water walking bugs are super hydrophobic, so that's to say the contact angle is getting close to 180, so it's very large. And they use exactly this technique. They're basically waxy and hairy, and the combination of the surface texture plus this intrinsic the contact angle, the waxiness, which brings the contact angle above pi by 2, makes them super hydrophobic. It's actually interesting because that was the very first experiment we did with bugs. Was to we were wondering how close they were to falling through the interfaces. We know that they're slightly heavy relative to water, so if they weren't water repellent, they would just sink. Right? If you put them underwater, they sink. So we thought, okay, well let's change the surface tension by putting soap in and see how close to the edge they are. Because we know putting in soap will decrease the surface tension. Yeah, exactly. Did that with Oliver Bueller, actually. So we put the soap in, and sure enough, they just fell right through the interface. And it wasn't for the reasons we thought at first. At the time, I sort of got into wetting through this, these biology problems, but it was because the soap changes the contact angle from greater than pi by 2 to less than pi by 2. So you suddenly go from something which is hydrophobic and rough, so super hydrophobic, to something which is now hydrophilic and super rough. So it goes from being super hydrophobic to super hydrophilic. So basically putting the soap in changes the chemistry, and so they become hydrophilic, then super hydrophilic, and the water just wicks into their roughness, right? So basically it goes whoop, right through, and so then they just sink through the interface. Of course, you can fish them out, and they clean themselves off, but it was quite striking. But it's a nice example of this effect, right? Basically the roughness. So if you can just so exciting things happen around pi by 2, right? You just go from being slightly above to slightly below, and you change the things massively, right? Qualitatively. Okay, so yeah, let's take a break.
Those bats must be very sensitive to pollution.
No, exactly. That's exactly. That's a very good point, and they are exactly. That if you have an oil spill or anything, then they're in all sorts of trouble. Or soap, chemistry, detergents, any chemicals will typically change by changing the wetting properties. Because there's a no, exactly, no. But there's actually, we did this thing on birds, and birds use, I'll show this to you later, but they use contact angle hysteresis to feed. So they actually, it's funny because we've seen here today this contact angle hysteresis is typically an impediment to drop motion, right? It causes drops to stick on slopes and so forth. But if you have a drop in a beak geometry, you can actually use this contact angle to feed. So it actually drives the drop up towards the mouth of the bird, and so that's what they do. And there was apparently some mass. I'm going to get in trouble here. Okay, can we stop? No, but there was some massive